Minasan, konnichiwa, Zamurai Engineer desu. In this video, we will continue our discussion on estimating the derivatives by numerical methods. And in our function, we are dealing with discrete function. On our module in this regard, we use our mathematics and we applied also the direct fit polynomial. So there are two ways we already able to present and discuss in terms of this type of discussion in this topic. Okay, so in this particular module, we are going to talk about Lagrange polynomial. So in this method, given coordinate x1, y1, and so on up to xn, yn, one can fit n minus 1 order Lagrangian polynomial given by this. So recall, the second method that we discussed in this regard is the direct fit polynomial. Okay, now we will use Lagrangian polynomial given by this one. So direct fit is p sub n, and Lagrangian polynomial is f sub n as a function of x is equal to summation from I is equal to 0 to the n of li sub x, li of x, and multiply by f xi. Okay, this is Lagrangian polynomial. Okay, where n in fn stands for nth order polynomial that approximates the function y is equal to fx. So we need to get a polynomial to the nth order that would approximate y is equal to fx, given at n plus 1 data points as x0, y0 coordinate, x1, y1 coordinate, and so on up to xn, yn coordinate. And li is equal to the product. Li is the product of the rational function from j is equal to 0 to the n of numerator x minus xj over quantity xi minus xj, wherein j is not equal to I. Okay, that is the meaning of L. That is the Lagrangian coefficient. Okay, so Lix, a weighting function that includes a product of n to the 1, n minus 1 terms, with terms of j is equal to I omitted. We do not like I to be equal to j. Okay, so all the other rational functions are included. Good. So take a look, take a note of this. This is difficult and maybe more difficult for others to understand. Okay, but one by one, step by step. Okay, take a look. The very important thing here is the first equation here, first equation. And all of this one and this one have definition. What are the definition given here? This one. Okay. That is the definition. And this one we have here and here. Okay. So those are just definition of what we can expect from these factors. So there are factors. Okay. Li and fx. Okay. So those are the factors. So let us continue. Then to find the first derivative, one can differentiate f sub n once. Because first derivative, you have to take the derivative once. For the higher derivative, we can take the derivatives correspondingly. Third derivative, we take the derivative 3 times, and so on. For example, second order Lagrange polynomial passing through x0, y0 coordinate, x1, y1 coordinate, y2, x2, y2 coordinate is. So if we have this only 3 coordinate, we have f sub 2 of x is equal to the rational function quantity x minus x1 multiplied by x minus x2 multiplied by f of x0 divided by quantity x0 minus x1 times quantity x0 minus x2. Okay? You will notice there is no x1 minus x1 or x2 minus x2 or x0 minus x0 because that is not allowed. That is what we mean by this condition. J is not J is equal to 1 omitted. Because if they are equal, for example, 0 minus 0, okay, that will become 0. And the whole thing will become 0. Okay? So that is omitted. That is the reason why you don't see anything with similar subscript. There is no factors here with similar subscript. X minus x1, x minus x2, x0 minus x1, x0 minus x2, x1 minus x0, x1 minus x2, x2 minus x0, x2 minus x1. There is no x2 minus x2. There is no x1 minus x1. There is no x0 minus x0 because those are omitted according to the rule. Okay, according to the rules. That is the rule. Okay, so it is easy just to follow this term and put up another term and put up another term. So step by step, you have to do this step by step. Otherwise, you will be overwhelmed. If you're overwhelmed by the greatness of the problem, okay, you will get confused. So do it one at a time. Do this first term, do the another term, and do the final term. So if we are looking at 3 terms, okay, 3 coordinates. If we are looking at 4 coordinates, there are 4 terms. Okay. If we are looking at n number of coordinates, we are looking at n number of terms. So anyway, we have to what? We are being asked to find the second order. So we have to take the derivative to find the to find the first derivative. Okay, so differentiating equation 2 give. If we take the derivative, taking the derivative of this equation, take the derivative of this equation. Is it easy or not? Those numbers with subscript are constant. That's why there are only what? 1, 2. That is what? A quadratic equation. That's only a quadratic equation. So it can be easily taken the derivative of a. Do you know how to take the derivative of a quadratic equation? So don't be amazed by this, no? So the variable is x and x. Okay, so if you multiply x times x, that is quadratic equation. X has an order of 2. So it is an easy matter to take the derivative of that. So if you are looking at this equation that without teacher that is explaining to you this thing, you will what? You will back out. You will back out from studying engineering. How difficult is this equation? Just looking at this equation, you will be afraid. You will be afraid. You just look at this equation. But I'm telling you, don't be afraid because x is one variable multiplied by another x, another variable. The answer is x squared. That is only a quadratic equation, and taking the derivative of quadratic equation is a simple matter. Okay, so this is the result if you take the derivative of that. Okay, okay. If you simplify that equation, this will be the result. Okay, you can try to practice that. Try to practice that. Try to practice your knowledge of calculus. Okay. So if you take the derivative of x squared, what is the derivative of x squared? 2x. Oh, here you can see. So you can see 2x. And all of the rest are what? Are constant. All the other numbers are constant. What are those, sir? What are those numbers that you are talking about? F of x0, this is constant value. x1 plus x2, that is constant. All of these are constant except x. This one, except x. Even the coefficient of x, which is 2 is constant. Okay? So if you take the derivative of this equation again, we are now looking at the second derivative. Okay? Clear? And therefore, second derivative of f2 of fx is equal to this one. Oh, what is the derivative of 2x? 2. Very simply, our second derivative would look like this, which are, these terms are all constant number, constant value, and therefore you can easily simplify. Right now, we cannot simplify it not right now because we still have to evaluate the value of x0 minus x1. What is that value? What is the value of x0 minus x2? But it can be easily done because if we know the value of x0, for example, 10, and we know the value of x2, for example, 5, or 10 minus 5 is 5. Okay, multiply by what? fx0, which can be evaluated. We can still evaluate that. For example, the value of that is 2. We can easily simplify all of this and we can get a final constant answer. This is a constant value. Okay? Clear? Are we clear? So let's have an example. Example number 3 for our third method. This is our third method. The upward velocity of a rocket is given as a function of time in table 3. Table 3 is actually equal to table 1 and table 2 of the previous example. Determine the value of acceleration at time 16 seconds using the second order. Second order meaning second derivative. We need second derivative. Using the second order Lagrangian polynomial interpolation. As the order increases, it will give us more and more accuracy. However, we cannot do it more than second order because, as we explained on the previous slide, if we get a constant value for the second derivative. If we get the third derivative, then derivative of constant is what? 0. So it is useless to use the third order Lagrangian polynomial. Okay. So it is useful for us to use instead the second order Lagrangian polynomial. So second order Lagrangian polynomial, it is the solution. So instead of using x, we just replace by t. Okay? So instead of using f, we just replace by v. So that is our first equation in your monitor. That is the first equation. So taking the derivative of that, so the same. We already know this. We are already familiar with this. So because t times t squared, derivative of that is 2t. Oh, very simple. Okay? Don't be afraid. Just repeatedly watch this video. Repeatedly watch this video. And what on learn by active listening. You have to be active listener. Okay? Listen carefully the lecture. Okay? So after taking the first derivative of the velocity is acceleration. That's what we need. Okay. Sir, why we only took the derivative one time? Isn't it the requirement of the problem to take the derivative, the second order derivative? Representation. We will represent the velocity function using second order, but we don't need to take another to take the derivative more than once, because the derivative of velocity is acceleration. The second order Lagrangian representation is this one. This is already second order. So this one. And we took the derivative one time, and therefore, what will happen? Just substitute the values. What is our value for t? 16. That is our target point. T 16. So acceleration at 16. So t is 16. Since t is 16, here all of the t here will become 16. Here. So there are what? 3. There are 3. So 1, 2, 3. So 3. What about T1? So we have 16, T1 here, and T2 here. T1, T0. So what did we use? We use 4. We use 4 points. We use 4 points. Therefore, T0, T1, T2. What? We use 3 points, no? T0, T1, and T2. Therefore, we use what? T0 is 10. T1 is 15. Okay, because we are targeting 16, we use T1 as 15 because it is nearer. What is the next one? 10. So 10, 15, and 20. So we only use 3 points here. While on the direct fit polynomial, we use 4 points. We use 10, 15, 20, and 22.5. But here, we only use 3 points because we are using second order Lagrangian polynomial. Okay? We use 3 points. That is T0, T1, and T2. Okay? So T0 is 10, T1 is 15, and T2 is 20. So you can evaluate. You can just simply substitute. And you will notice, sir, what is the value for velocity T0? Velocity 10 is given. Velocity T1, sir, is velocity because T1 is 15. That is velocity at 15. That is given from the problem. T2 is velocity 20. That is also given in the problem. From the table, there is a table. Diba? Table, time versus velocity, table. Those are given. So all of these are constant given. So the only variable here is the variable t. But since we are being asked what is the acceleration at 16, so our variable t would be 16. So therefore, we can what? Evaluate, and the answer would be 29.784 meter per second squared if we use the Lagrangian polynomial. I think this is the last slide. So this is the given table. So what is the value of velocity at 20 seconds? That is 517.35. That is given here. So this is 517.35. T2 is Okay. Excuse. So we use the second order Lagrangian polynomial in this. Yeah. So all in all, when tackling the problem against the discrete function, we can use three methods. We can use the simple interpolation method, okay, and then we can use the direct fit polynomial method, and we can use the Lagrangian polynomial method. Okay, so this one. So here's the Lagrange polynomial. Okay. So this is the way we do it. So don't be afraid with this definition, because this definition, this Li as a function of x, Li is a function of x, product of this one, these are the Li. This one, this rational function is the Li. This is the L0, L1, and L2. Okay? Because we are using the second order Lagrange polynomial, L0, L1, L2. We have L0, L1, and L2. Okay? Don't be afraid. This is very simple. Very simple. And in actual problem solving, Li is this one, this one, this one, this one. L0, L1, and L2. Li meaning I is from 0 to N. N is 2 because 2, second order. Li from 0 to N. Okay? If you can back here, here. LJ. I and J doesn't matter. Doesn't matter if you use I or J. What do we mean by this? Product of this term from 0 to N. Our N is 2 because we are having the nth order here. Nth order. Okay. Second order, the N is 2. 0, 1, and 2. So here, we will have 0, 1, and 2 here. Okay. So therefore, our I is from 0 to 2. Okay. For example, here, you'll notice N. N plus 1 total data. So if we will use second order, N is 2 here, plus 1, that is 3. 2 plus 1 is 3. So therefore, there are 3 terms. What are the 3 terms? L0, L1, and L2. Those are the 3 terms. So that's why here, it's clear. It's very clear. Okay? It's very clear how to use this beautiful technique. This is a little bit complicated if you are new to this method. But it is better than the direct fit method. Okay, it's better than the direct fit method. So take note also of the answer. I would surmise that the answer of this example is better than the other methods. So the answer on our simple interpolation method is what? Let us, the answer is 30.914. Answer for direct fit method is 29.664. So our answer is 29.7 meter. I think this is nearest to the true value. You can find the error, which one is the best method. Okay, any question? Please use our comment section below. Again, this is Dr. EYPEI, preaching engineering for nation building.